All right, now yesterday we just reviewed the stuff you needed to know for the writing nuclear symbols, basically. Protons, neutrons, electrons, the particles that make up atoms. All right. Today we're going to start talking about the real nuclear chemistry. Okay, we're going to do quite a bit. We have a double today, so we'll be doing two things. First, let me just say, any nuclear equation, any nuclear change is going to involve a change in the atomic nucleus, not what you've been seeing for the past 7 months. Okay, 7 or 8 months have gone by. We're almost done with the school year, and you have never seen this happen before. Every other chemical change you've seen throughout the year has involved changes with what particle? Electrons, and electrons only. Okay? Every other change was a guy losing an electron, gaining electrons, sharing electrons to make new compounds, or compounds being broken up by changing their electrons. But one of the first things I told you back in the day was that, sodium chloride yields sodium plus chlorine. Okay? I have to have the same number of atoms. I can't create or destroy atoms. I can't change atoms. One sodium over here better be one sodium over there. 2 chlorines over better be 2 chlorines over there. Well, that's going to be different now, because this does not involve changes with electrons. Chemical reactions involve changes with electrons. Nuclear chemistry involves changes with protons and neutrons, and you will get new elements. You will change the identity of an element. Because I hope you remember this. What makes you remember me doing this as how many times have I done this? I take away a carbon. I take away an electron from carbon. I call it a carbon what? An ion. If I take away a neutron from carbon, what do I call it? A carbon isotope. I take away a proton from carbon, what have I made? Boron. And that's a nuclear change. We've never done that before, but that's all we're going to be doing in nuclear chemistry, is changing the identity of atoms, which is kind of crazy. All right, we've never been doing that before. All right. Okay. Well, I'm going to start off with what I want to talk about first is this nuclear binding energy, what holds the atom together. And to do that, I got to talk about the mass deficiency and what's going on here. He didn't go into this much detail in the little funny little clip for the movie, but that nuclear binding energy, you can find out about that as he kind of implied, because the masses of the particles after they're they undergo this change weren't the same. They weren't what they're supposed to be. All right, it's kind of weird, but if you add up all of the parts of an atom, they don't add up to what the atom really weighs. So, the sum is not equal to the whole is not equal to the sum of its parts, which doesn't make any sense. If I were to add up each of your individual weights, you would weigh exactly the same amount as the class if I put you all on a scale at the same time. But that's not the case with an atom. All right, it's kind of weird. The mass deficiency is the difference between those sums. The difference between the sum of the masses of all the protons, neutrons, and electrons and the actual mass of the atom. The actual mass weighs less than it should. That's the crazy part about this. And I can show you that with a simple calculation. We're going to do a calculation on that. That missing mass is what's the energy that holds the atom together, that nuclear binding energy. That's what that missing mass represents. Now, I'm going to have to give you a lot of information. I'm not going to expect that you memorize all of it. In order to do this calculation, you're going to have to know the charges of each of the individual particles, the protons, neutrons, and electrons. We're going to have to add them all up and multiply by how many we have. And I'll have to give you the actual mass of an atom. Obviously, I don't want you to memorize that the proton's mass is 1.0073 atomic mass units and neutrons are 1.008. You don't have to do that. All right? That's a waste of time. So I'm going to give them to you on the sheet, along with some other stuff on the sheet we're going to be using as well. All right? But basically, that missing mass represents, it's what holds this guy together. That's the nuclear binding energy. It represents the binding energy that holds the nucleus together. Now I'm going to pass these around. You're going to need them in a second while you're copying that down. Then we're going to do an example. Oops. These are the masses. Do not need to write these down. They're on the sheet I'm passing around to you, although it seems I'm not printed all the way out. Do copy this down, though. Copy this example down. Okay? While you're copying that, let me look for those other ones. I didn't give you these yesterday, did I? They'll be around here somewhere. Oh, there we are. How many more we need here? Have one. Did I give somebody else too? Any extras? Leave extra out. Somebody was going to be absent. Where they are. Oh, here's one more. All right. Now let me show you what I'm saying here. Okay, we're going to do this calculation right here. Okay, you watching? That's what we should get when I add up all the particles, protons, neutrons, electrons that are in chlorine 35. So let's do it. Let's add them all up. How many protons are in chlorine 35? 35? No. You have to look at the periodic table, 17, right? So 17 protons times, what's the mass? I just gave you the sheet. What's the atomic mass of a proton? 1 point what? 0073 AMUs. Do the math for that one, Jared. While he's doing that, let's do the neutrons. How many neutrons are in chlorine 35? 18. You have to subtract 17 from 35. 18 neutrons times 1.0087, is it right? Is that correct? Do the math for that one, Zach. And while he's doing that, let's do how many electrons. How many electrons are in this guy? Well, if it's a neutral atom, he's got 17 protons. How many electrons does he have? 17. 17 times, what's the mass for the electron? No. Mass for the electron?
Well, it's insignificant.
Oh, it's inside the notation? Okay, what is it again?
5.46 times 10 to the negative fourth.
Negative fourth. All right, that makes it 0.000546 then, right? 5486. 5486. Is that right? Or is it 546? 5486. Okay. All right, do the math for that one, Ellie. And let's get these answers for these here. First one was what?
17.1241.
So 17.234. 5 significant figures. 17.124, right? And for the next guy, 18?
18.156.
18.156 AMUs. And the last one?
9.3. I did say.
I'm sorry, what is it?
9.3 times 10 to the
Negative third, so 0.0.
0.
What was the numbers again?
0.0093.
933? Okay, AMUs. There's nothing here. That's not a 1 there. It's just nothing. Okay? Add all those up. See what we get. What does the summed mass come out to be? This is the summed mass. What do we end up getting? Did you get 34? I'm sorry, 0.9, 34? 35. 35.29 maybe? 290 or just 29? 0.290? Or
I got 0.28.
289? Okay. 0.289. That looks good. Does everybody else get that? All right. Now here's the key to this. 35.289 is what they should weigh. That's what an atom of chlorine 35 should weigh. Doesn't. It weighs 34.9689. You can weigh this. You can put it. You can measure it. So how are you going to get the mass deficiency? The difference between them? You simply subtract 34.9689 AMUs. And what do you get for your mass deficiency? How much is missing? It's not a big number. What is it? .33201, so 0.320 for significant figures, because this guy's only got 3 decimal places there. Now that may seem insignificant. Well, geez, that's pretty close, 0.320. You know, who cares? That can't possibly be worth much. Actually, wait till I show you how much it's worth. I want to show you how much energy is involved in that. Okay, how much energy there really is there. If all of that mass, remember, we're going to use. What equation do you think we're going to use to be able to figure out how much energy that's equivalent to? Yeah, Einstein's equation, E equals mc squared. That may look like a really small number, but it's not. All right, you're going to see that it actually is a very large amount of energy in that very small mass. Okay, watch. I'm not going to erase that. I'm going to come back to that in a minute. The second part of this problem is getting the nuclear binding energy. Now, the nuclear binding energy, there's 2 ways you can look at this. Okay? The way the video showed it, it said it this way. The nuclear binding energy is the glue that holds the nucleus together. And it is equivalent to that 0.321 for 0.320 for chlorine 35 atom. The equivalent of that much mass. Okay? Here's the other way you can look at it. It's the amount of energy it would take to completely separate out each individual proton, neutron, electron from the atom. Okay? Because it's going to be the same amount. All right? So either way you look at it, it's the same value. It's the amount of energy holding the guy together, or the amount of energy it would take to rip them apart. You know, we all know conservation of matter and energy is going to be the same number. So it's the amount of energy it takes to completely separate an atom into protons, neutrons, electrons. What's holding this guy together? How would I calculate the nuclear binding energy for chlorine 35? Which is what I'm going to use that equation, E equals mc squared. And there's only one variable in this equation, m, which we know. We're going to solve for E. C is a constant. Okay? What was the m? We just figured m out in the last problem, 0.320 AMUs. But hold on a second. For a reason, I don't want to use atomic mass units. I want to use a number that will actually, in the end, I'm going to see if anybody from physics class recognizes it. Okay? I want to use a number. I want to have, instead of atomic mass units, I want to have kilograms. How are they related? Well, they're related very easily. One atom of chlorine 35 contains 0.320 AMUs of mass that's missing. Okay? That's how much energy there. If it was a mole of chlorine 35, what would that number be? One atom of carbon weighs 12.011 grams. I'm sorry, 12.011 AMUs. One mole of carbon weighs 0.011 grams. Yeah. So this is the same number in 0.320 grams if it's talking about moles. That's how many grams there are per mole. Okay? So I'm going to use that number instead. Calculate the nuclear binding energy for chlorine 35. Well, for 1 mole of chlorine 35, it takes, it's missing 0.320 grams per mole. which for a reason, I'm going to convert to kilograms. How would I convert that to kilograms? Again, you're going to see why I'm doing all this at the end. Maybe some of you will see it. Convert that to kilograms, grams at the bottom, kilograms at the top. 1 kilogram contains 1,000 grams. That's an even smaller number, 0.000320 kilograms per mole. That's the mass. How much is that? That's such a small mass. That's less than a paperclip. That's how little mass that is. For an entire mole of chlorine atoms. An entire mole means 6.022 times 10 to the 23rd atoms of chlorine. You're going to have less than a paperclip's worth of mass. Just a fraction of a paperclip. That doesn't seem like a whole lot of energy holding this mole of chlorine together. Let's plug them into this equation, though. E equals mc squared. And let's look what happens. Two things are going to happen. One has to do with what's going to happen to the size of the number. The other thing has to do with what's going to happen to the units when I'm all done. The mass is 0.000320 kilograms per mole. Oops, per mole. And does anybody remember what the speed of light was from earlier in the year or from Schrader's class? 3.00 times 10 to the 8th meters per second. It's actually 2.99789 or whatever. It's a long number. We're going to use 3 to make it easier for the calculations. And that number is squared. Do the math for that. Don't forget to square the 3 times 10 to the 8th. Did you get like 2.89 or something like that? 2.88? Okay. So the amount of energy is 2.88. And look what my units are going to be. Kilogram meters squared per second squared per mole. Now, why did I make those units kilograms and when I'm all done have this come out? Does anybody from physics class recognize what a kilogram meter squared per second squared is? It's a joule. It's a joule per mole. Then 2.88. Oh, by the way, it's 2.88 times 10 to the what? I forgot to write that down. Sorry. I got all excited there. Let me just do that again. So is 2.88 times 10 to the what? What was it? 13th? 13th kilogram meter squared per second squared per mole, which would be 2.88 times 10 to the 13th joules per mole. That is how much energy holds together a mole of chlorine atoms. How much energy is that? That's enough energy to basically boil and totally evaporate Evansville Lake, all right, the entire lake. Evaporate it, vaporize that lake. It's an incredible amount of energy holding, even though it seems like it's a small mass. If you convert all of the mass to energy, because of that squared function, for such a large number, you're taking a very small mass and it's a lot of energy in there. Okay, which is why our power plant is so energy, uses fuel that's so energy dense. I mean, this little, when we talk about the power plant in the future, next week probably we'll start talking about them. This little pellet contains enough energy of, it says it on here, 1 ton of coal. All right, that's the equivalent of the energy you would get from burning 1 ton of coal. Why? Well, first of all, even this, by no means, at the end of when that fuel pellet's spent and it's done, you did not convert all of that fuel pellet into energy. Believe me, that'd be way more energy than this. But because you are tapping into that nuclear binding energy when it decays, when you make it undergo a chain reaction, you are getting a great deal of energy from a very small mass, as you can see here. Okay. All right. Now, if you look at the bottom of those worksheets, the same sheet I gave you a minute ago, you will see questions on the bottom of that. You see them? That are 1 to 5. That's your homework. I'm going to give you a few minutes to start on that right now. Those 5 problems are your homework. Well, we're going to